Hi there, this is Jacob Nash Engineering Lessons, and this is Unit 4.1, Lesson 1, and this unit is on probability and statistics. So, let's look at this. You might think you already know what probability is, because you learn it a little bit in elementary and middle school, and some math classes there, which you still might be in middle school when you're taking this. I don't know about your situation, but anyways, there's more to it, obviously. Like with anything, if you think you've learned it, well, there's going to be something new that you didn't learn. So, here are ways to calculate probability, but first let's just look at the actual definition. It's the calculated likelihood that something will occur. So, when you learned it in elementary school, it's just like likely, unlikely, very likely, possible, things like that. But this time we're actually going to put some numbers to it, which you may have done before, but we're going to use some equations that you may have never used before. So you can determine it by using empirical data, which is an observation. I see this, so something like that. Theoretical is when you use known elements. So if you're doing the probability of a coin or a die, then you already know that there's 2 sides on a coin and 6 sides on a die. Subjective data is just like assumptions. I think that. But this is a little bit less accurate, but this is just what you have to do sometimes if there's no numbers. So like, what's the probability that a car will crash into your house? Unlikely, hopefully, unless there's a lot of crazy people around where you live. But that's subjective because there's no numbers to that unless you have data to prove it. You can find relative frequency by using this equation, which you probably have used before even if you don't recognize it, because when you say there's a 1/2 chance that you'll get heads on a coin when you flip it, you're using this equation, you just don't think about it. So F is the frequency, and NX is the number of events with a desired outcome. That's one event, that one side of the coin you want. And then number of outcomes, it could be heads or tails, so that's 2. 1 divided by 2, 1/2 chance. So let's see, what's the probability of flipping a coin 3 times and landing on heads 2 times? This might seem complicated, but when you think about it, it's really not. Let's look at this thing with a bunch of H's and T's. So let's say at this point, let me get the pointer. At this point is where you first flip the coin. What's in red is roll 1, what's in yellow is roll 2, and what's in green is roll 3. So you can either do heads or tails on the first roll. On the second roll, depending on what happened on the first roll, you will get heads and tails again. So you see, if the first time you went on heads, then you could get heads and tails. But if you went on tails, you could still get heads and tails. And then roll 3, it splits up even more. So it's kind of, if it looks like a family tree a little bit, because it keeps growing exponentially. And there's 8 outcomes total. All the green ones are the final outcomes that there could possibly be. There could be heads, 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 tails, or heads, heads, tails, heads, tails, heads, heads, tails, tails. It's just all the possible combinations. So there's 8 outcomes, but there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 possible outcomes that could occur. Well, I mean, there's 14 combinations. There's 8 outcomes. But that doesn't have to do anything. We're looking at 8. So how did we get 3 desired outcomes? We wanted to have it land on heads 2 times. So I circled in different colored rings all the times that there's heads, which I didn't circle these because they have to be next to another one. So here's the first possible outcome that's desired. You could get 2 heads if you went heads, 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 or heads, heads, tails. The second possible outcome is these 2 heads that are beside each other. And the third possible outcome is that one, but there's no more, so we have 3 outcomes. and then you do 3 divided by 8, which is 0.375, which is 38%. So that's how we got that. Now, we need to look at the exclamation point in math. If you've ever seen this, you might have wondered what it is, if you've never learned it before, but it's not really that complicated. But it can lead to big numbers. So, this symbol means factorial. So whatever is before the exclamation point needs to be multiplied by each integer below it. So if that didn't make sense, look at this example. If you have 4 factorial, now you say 4 factorial, you don't say 4! You don't yell it. That's not what that means. That's only in normal writing. You don't have to yell that. Just say 4 factorial. So you go down by 1 until you get to 1 itself, and you multiply by all those things. So 4 times 3 times 4, 4 times 3 times 2 times 1. And then if you had 5, it would be 5 times 4 times 3 times 2 times 1. But like I said, it can lead to big numbers, because if you had 100, it would be 100 times 99 times 98, all the way down to 1. So 4 factorial equals 24, because 4 times 3 times 2 times 1 equals 24. So that's what that means. And why we said that is because it's in this equation that we're about to use, which this equation looks really complicated, but it's not really. You just have to find 4 things: n, x, q, p, lowercase p. But uppercase p is what you're finding in the end, which is probability. So this is the probability equals n factorial divided by x factorial times the difference of n minus x factorial, and all of that is multiplied by p to the x power times q to the n minus x power. So that looks complicated, but when you find all the things that you plug in for these numbers, it goes quick. So uppercase P is probability. So there's 2 P's in here. Remember, though, they're not the same thing. X is the number of desired outcomes. So we already had an equation like that when we were doing relative frequency. N is the number of trials. P is your probability of success on a single trial. So you'll use this if there's multiple trials. Q is probability of failure on a single trial. And exclamation point is factorial. So remember, it's not n, it's just n factorial. So we're going to look at the same question we already looked at with the coin, but this time we'll solve it by using Bernoulli process. Sorry if I completely forgot to even say that in the last slide. Now, we already know the answer is going to be 38%, but how do we get to that? In the equation that's back here, we need to find all the variables in there. N, we see n, x, p, q. That's what we need to find. So what's x? We said that was the number of desired outcomes. Last time, remember that was 3, but that was only when we were using the relative frequency equation. But it's 2 this time because we want to land on heads 2 times. And in this case, we would use 2 for x. There's three trials. Remember, that's the number of trials, so 3. What's the probability of success on a single trial? Well, it's going to be 0.5, because that's when you flip a coin, there's 2 sides, so 1 divided by 2 equals 0.5. And same thing for probability of failure. When it's a coin, P and Q are always going to be the same, but that's not the case for a dice. So now we plug in the numbers. So we had to have n factorial, which is 3 times 2 times 1, divided by x factorial, 2 times 1. And remember, if you don't understand what factorial means, please rewind the video and go back to that slide. And And then we have, once again, n factorial minus x factorial, or sorry, it was just x, never mind. And then we do squared because it was to the nth power. Nth. Then this comes out to be 6. This comes out to be 2, and then 6 minus 1, and then 0.25, 0.25, and then 2 times 5. This ends up being 2 times 5, which is 10. 6 divided by 10 is 0.6. 0.25 times 0.25 is 0.0625. 0.6 times 0.0625 is 0.375, which equals 38%. Also, it could be 37.5%, depending on what your answer needs to be. So, sometimes you also have to do multiplication. If two events are not dependent on each other, then multiply separate probabilities to find the probability of both occurring. So if you want to know what's the probability of rolling a 4 and then a 1 in sequential rolls, so they're not dependent on each other. Not dependent can be represented with n th, that's a Icelandic letter. So, but you can just say not dependent. You don't need to say n th. So, if the probability of A happening is not dependent on the probability of B happening, then the probability of probability of A and B happening equals A times B. The probability of A times the probability of B. So going back to this, first we need to find the probability of rolling 4, 1 out of 6. Then a 1 is also 1 out of 6. You multiply those, you get 1 out of 36, which is about 3%. Thank you for watching, and that'll be it. Hopefully this helped, and feel free to ask any questions below. Maybe I'll be able to answer them, but if not, then hopefully someone else will. Thank you for watching.